So in the previous power lecture, we discussed that to minimize the loss function A of W, which was simply the this L2 norm, we select the function in the majoration minimization algorithm gk as this function. And now here we'll minimize this function g of k by setting its gradient to 0 with respect to w. So first we'll expand all these terms to compute the function gk. So we can expand it as gk of w is y transpose y minus twice of y transpose times phi of w minus plus w transpose phi times w. Now we'll expand this term, so this would become w transpose beta I minus phi transpose phi times w minus twice of wk transpose times beta I minus phi transpose phi times w plus wk transpose times beta I minus phi transpose phi times wk. So this gives us, so this term is cancelled by this term, right? So you can cancel out this, so this would be cancelled, and the resultant function we have is beta times w transpose w. So we are taking this term plus, so we are done with this term completely, plus this term y transpose y minus, so we are clubbing this term with this term, so we get minus twice of y transpose phi plus wk transpose times beta times I minus phi transpose phi times w. So we are done with this term and this term. So now only this term is left, plus wk transpose beta I minus phi transpose phi times wk. So we can further simplify this term by writing it as beta times w transpose w. This is a quadratic term. So you can see in the quadratic term the phi transpose phi is gone. We are just left with the quadratic term as w transpose w minus twice of y transpose phi plus wk transpose times beta I minus phi transpose phi times w plus y transpose y plus wk transpose beta I minus phi transpose phi times wk. And now we can see that this is the quartic term in w, this is linear in w, and the last term doesn't even depend on w at all. So this is just some constant which we can denote by ck, where we have substitute k to denote its dependence on wk. But since wk is a constant, phi is constant, beta is constant, and y is also a constant, this entire term is constant, it doesn't play any role in the optimization problem, and that's why we can club it together and call it ck. So we can write the function gk as gk of w is equal to the quartic term beta times w transpose w minus the linear term y transpose phi plus wk transpose beta I minus phi transpose phi times w plus some constant ck. We could have directly computed the derivative of this function gk and set it to 0 to obtain the solution, but first we have simplified the definition of the function gk because it will become very critical later on, and that's why we have represented the function gk compactly to show its dependence on w, and this constant term is being ignored. So now we can set the gradient of this function to 0 to obtain the solution or the minimizer that minimizes this function g of k. So the gradient of this term of this function is simply equal to twice of beta times w minus transpose of this term. So this would be twice of phi transpose y plus beta times I minus phi transpose phi times w. Okay, sorry, superscript. And we set it to 0 to obtain the solution as we get w equal to wk, we are taking this term into account, wk plus phi transpose y minus phi times w. Okay, so we just took the phi transpose as common out and then the division by beta. So we just cancel the 2 from here. We take this to the right hand side, this entire term. So this the right hand side becomes like phi transpose y plus beta times wk minus phi transpose phi times wk. So we just like the beta would cancel for this term, so we have wk, and then division by beta for the rest of the term, this would be over beta and this would be over beta. I just took the phi transpose common, and inside we have left y minus phi times wk. So we get the solution as W equal to Wk plus 1 over beta times phi transpose times y minus phi times Wk. So this Wk, this solution now become Wk plus 1 that minimizes the function g of Wk. So now applying this algorithm iteratively, for example, how do we use this solution? So as we discussed in the previous part, the pseudocode of the MM algorithm. So we just start with any W naught, we select it randomly, and then we just do this update. Wk plus 1 goes to Wk plus 1 over beta times phi transpose y minus phi times Wk. And this solution is guaranteed to minimize the original loss function A of W. And as you can see, the earlier normal equation based solution required us inverting a matrix phi transpose times phi, whereas this solution just requires the multiplication with the matrix phi transpose and multiplication with matrix phi. It requires no inversion of any matrix at all. And this iteration is known as Landweber iteration. So we can use it to minimize the linear regression, to compute the optimal parameters W for the linear regression problem as well. And it has much faster convergence as compared to the gradient descent algorithm. And the advantage of this solution over the normal equation based solution is that it doesn't require inverting any matrix, it just requires multiplication with matrix phi transpose and phi.